Hello everyone, welcome to my first video lab report. In this lab, the goal was to observe the motion of some object that is moving at the same speed without changing direction. In this lab, I compared the position of an object as a function of time for an experimental measured position and a computational model predicted position. The computational model used Newton's second law to predict the position. And I found that the model position matched up very closely with the experimental position. And so how this lab utilized Newton's second law is that Newton's second law states that final velocity equals initial velocity plus F net divided by mass times change in time. Now, assuming that the velocity is constant, this means that final velocity must equal initial velocity, so the F net must be 0. And then you can calculate the position if F net is 0 with the equation final position equals initial position times velocity, which is constant, times change in time. And so for the experimental observations, I recorded a video of my chapstick rolling across the table and took samples of the positions versus time as it rolled across the table using the tracker software. And from that tracker software, I gathered information like the initial position, which is located at 0.16 at t equals 0. And then I took a secondary position measurement and used that to calculate the initial velocity, which is in the negative x direction at going 1.21 centimeters per second. I also measured the last time observation, which the observation stops at time t equals 0.567. And I also found the mass of the chapstick because it was written on the side of the chapstick. And then additionally, the axis was set on tracker so that the positive x direction went to the right, and this caused the initial velocity to be in the negative x direction. So if the axis were switched, then the initial velocity would be in the positive x direction instead of the negative x direction. The speed of the chapstick would not change, only the direction with respect to the axis would change. For the computational model, here is my code, and I edited a few things to make it resemble the chapstick. First off, I changed the mass here and then put in the initial position and the initial velocity. And then in this line, this is setting the net force to 0. And given Newton's second law, the velocity is only constant if the net force is 0. And down in this line, it shows the equation of where Newton's second law is applied to the model. And when you run the program, it looks like this, basically plotting out the position over time and shows sort of like the ball moving in the same direction. And I compared my computational model to my experimental, and these are how the two matched up. There are a few differences, and I think this is likely caused by my camera angle that I was filming from, especially down at the end of the graph. There's a lot more differences, and that's just because I guess I shifted the view. So in order to improve this experiment, I would probably use a tripod or something that can stabilize the camera, or maybe use a higher quality camera where I can take more frames per second and get a more accurate detail of the chapstick's position over time. And is it possible for you to say how many pushes and pulls are added together to give a 0 net force in the case that you observed? So basically, here are some of the forces that are acting on the chapstick. There's the gravity, normal force of the table, the push, and the friction. The normal force of the table cancels out with the force of gravity and has a net force of 0. However, the force of friction in the experimental does not cancel out with the push. It actually slows the chapstick down over time so that the net force is not actually 0 in the experimental side of this experiment. But with the computational model, there is no friction, so that has a net force. And this could also explain why there are some differences between the computational model and the experimental observation. Thank you so much for watching.